Welcome back, everybody, to the second part of this lecture. So where were we? We saw that we can interpret every document as a vector of positive real numbers, and that means we can interpret a document as a point in a vector space, in the first quadrants of R to the power of m. We saw that we can renormalize a vector with the Euclidean norm, so that means you can do that sort of things, and this is how you get something just between 0 and 1, such that the sum of the squares gives you 1. Okay. Now, there is something else that we can do. So I mentioned that the Euclidean norm is based on the inner product, the fact that you can have you can take the square root of the inner product of a vector with itself, but it doesn't have to be with itself. You can also compute the inner product of any two vectors. And when you do that, it actually gives you a measure of the angle between the two. Right. So if you take, in that case, let's call them x and y. So if the inner product is the dot product, it's just the sum of the pairwise coordinate product. And then you get, if you do it on the renormalized vectors, so all I did here is I divided by the norms of x and y, that actually gives you the cosine of the angle. Who knew that? You know that, right? Who didn't know that? Okay. So who knew that the dot product or the inner product gives you something that tells you about something about the angle, right? It's 0 if it's perpendicular, and it's 1 on the renormalized vector if they are the same. Okay, awesome. So basically, that's the cosine of the angle, and that's a similarity measure, right? Because if you have two documents that are very almost the same direction, cosine is almost 1, then these documents are similar. And if the angle is very large to the point that it's perpendicular, then these documents are very dissimilar. Right. The most dissimilar the documents can be to get 0 is basically, since you already only have positive numbers in there, it means that the terms do not intersect at all. This is what it means. You have two documents that are completely different. They have no term in common. Then you get this inner product that is actually 0. It's not true in general. If you can have negative numbers, that's not going to be true. But since we have positive numbers, it's working here. Okay, so it's a very good quantification for the similarity. Does similitude exist? I will check if similitude exists. It might be that it exists, but similarity, I'm going to say. Very similar documents are like this, right? Similar direction, not equal, but similar. And very different documents are like this. Note that the norm of the documents doesn't matter. I project them all on the unit sphere, right? So the only thing that matters is the angle. It's not the norm. You could have the documents that are very similar and far away in terms of distance if they only differ by the norm, right? And these are documents here that would be very different. These two would still have terms in common, but maybe not so many. Okay. So now, if I look back at my entire collection, so I would have all of these dots, all of these points in my vector space. What are queries then? Well, queries are the same. Queries are also bags of words. You also type words in a search engine. So it means that even a query corresponds to a vector. So we can not only plot the documents in there, we can also plot the queries. Do you see where this is going? If we can also put the queries in there, then we can actually evaluate the queries by just looking at the documents that are similar to them. In other words, the documents that have a small angle with the query. So you see query 2, for example, here is a good result, has a good result with D3, document 3, because the angle is very small. And the same for query 1 here, you probably want to return D1 and D2. Do you see how that gives you a scoring system? Now, given a query that is a point in here, you just order the documents by increasing angle, and that's it. For whom is that new? Right? And intuitive? Okay. So now we are back to how we do this, because we need to compute these inner products for every document together with the query. But remember that we are looking at a vector space with dimension 500,000 or dimension 1,000,000. That's a lot of computations to do, right? You need to do that for every document and within the document for every term. So that can be a lot of things to compute. right? Very scary if you consider that m is actually 1 million. Do we really need to do it 1 million times? Is it really a sum over 1 million numbers, 1 million products? Yes. Do we have the microphone? Is it working now? Maybe you can try the batteries. I think there was a battery issue earlier. Back here. We can try to put the batteries again and see if that works. All right. Oh yes, that light is green. Yeah. Okay, so let's try. If you can speak in the microphone. Wow, you're good at that. Okay, go ahead.
Most of the entries will be 0 for our query.
Yes, this is absolutely true. And the reason is that the query has a limited number of terms. The books are large. If you have a book, that's a lot of words, right? But the query that you type in Google or Bing or DuckDuckGo or whatever, that query is going to be short. So it means that you don't actually want to sum over a million terms here. You only want to sum to as many terms as there are in the query. That already is looking better. Right? Because now if the query has 4 terms, then we only compute the inner products based on these 4 terms. Okay, so this is reassuring because otherwise doing it with a billion documents multiplied by 1 million terms, that would have been close to impossible. Okay, so we need to compute this inner product as a measure of similarity. We also need to renormalize. That's also going to have some cost, right? To renormalize the inner product. It's not just the inner product, it's divided by the norms of the vectors. So now let's just put in what it's actually, because now I just used x and y, xi, yi for the coordinates, but what are the coordinates? It's the TF-IDFs, right? So I can just put back the TF-IDFs by default. So it's the multiplication of the products of the TF-IDFs divided by the norm of the query and the norm of the document. Okay. So now that we have this concrete formula, we can try to look again at this index here and figure out how we can compute this scary product of this scary sum of products of TF-IDFs with the standard inverted index. So first, we need to store the TF-IDF somewhere. Right? This way. So we could, as a first idea, say, okay, we put the TF-IDFs in every postings. Every posting corresponds to a TF-IDF. So we just put them in here. We could pre-compute them and store them here. The problem is that TF-IDFs are not integers. They are actually more like doubles or floats, right? Real numbers. The problem is that we can only compress the index if we have integers. So there are many considerations here that it's not so easy that you can just put real numbers in there. In fact, it is possible to also have an equivalent of the gamma encoding for real numbers. I actually found a way to do that. That's anybody, I can share the link if you want. It is possible, but in practice, we actually don't want to store floats or doubles in there. So what we do is that we only store the TF part of the TF-IDF, only the term frequency. That's going to be an integer. We can store it along with the document ID, right? So the document ID plus the pre-computed term frequency. And we can put the IDF part in there. That shouldn't be very surprising to you, right? Because the purple part that I showed until now, that's the document frequency, and that's just log of n over the document frequency, right? So that shouldn't surprise you that we put it in the purple zone. And what we do in practice, and I'm actually not entirely sure why this is done in practice that way, we don't store the log of n over df, we store n over df. And somehow the log is computed on the fly. I'm not exactly sure why, but it seems to be what a lot of people do. Another alternative would be to directly store the log of n over df, right? Okay. And then so that's for the document side. So that's the term frequency for the document side is stored in the postings. The IDF on the document side is stored in there. The TF, the term frequency for the query, that's something you can do by hand on the fly with the query. Simple enough. Just look at the query and count the terms in there. It's so small that it's very quick to do. And the IDF of the query, that's also easy, right? So you can also compute it easily. So now that we've done that, we have stored the TF IDFs a bit distributed, you know, the TFs there, the IDFs there, and so on, but now we've stored them in the standard inverted index. So now we should have everything we need in order to compute this horrible thing, okay? So the way this is done, if you look at what that computation is about, it's a sum over the terms of the products of the TF-IDFs for each document. So that's two-dimensional, right? It's the terms and the documents. So what we can do is we put data structures in place. We call them accumulators. We put one bucket for every document, starting at 0. And every document that there is in the system, in that case, I have 7 documents, so I put 7 buckets. These are accumulators. And I'm going to just populate them as I traverse the index. So it means that I'm going to compute these, let me show again the formula. So this part of the formula here, technically the mathematical term for this here is term, but then that's going to be confusing because we also use term for the words, right? So I'm not sure exactly how to call it without confusing you, but basically this is the thing that we need to compute for every term and for every document, right? Let's call it the thing. So the thing, we're going to compute the thing here for every term and for every document. So where do we get that thing from? Well, we just need to look at the individual components, right? So the query norm, we can compute it. The TF of the query, we say it's computed on the fly for the query terms. IDF, it's stored in the purple squares, and then the TF is stored on the blue squares with the postings and so on. And the document norm, you can also pre-compute separately for every document. Okay, so this is where it comes from. And what happens, by the way, you can just square the IDF, right? You have twice the IDF of the term, so you can just do that. All right. So basically, whenever you have a term in a document, you compute this thing and you accumulate it, meaning plus, into the accumulator for document D, right? In that case, it's 4, so I put it in the bucket 4. You just need to do that for every term and for every document, right? So there's 2 strategies for that. Either you do it term by term. You start with a term and then do it for every document. Then you take another term and do it for every document. Or you do it document at a time, meaning that you do it document by document, starting from the left to the right. And then for every document, you go term by term. So there are these 2 strategies. They both work. This strategy would be closer to the intersection and union algorithms, right? Because this way of doing things is just from the left to the right, similar to intersection and union. Let me show you both because I prepared animations for you. So let's start with term at a time. So term at a time is this strategy. First the terms and then the documents. So term at a time means, in that case, let's assume the query is ETH Zurich computer. So I'm starting with ETH. And within ETH, I'm starting with document 1. So I compute this thing for ETH and 1, and I find some number that I add to the bucket 1. Then I compute the thing for ETH and document 2, and I accumulate it in bucket 2. Then I compute the thing for document 3, accumulate it in bucket 3. Then I compute the thing for document 5 and term ETH, put it in bucket 5. Then I compute the thing for document 6 and ETH, put it in bucket 6. Now I'm done with term ETH. I go to term Zurich. Then I do it again for document 3 and for document 4. So you see it adds, that makes it higher. I add and contribute to the scores. Then computer, again, document 1, document 2, document 4, document 4, 5. And now I'm done. Now you can say what document gets returned first, right? So going to be document 5, then document maybe 1 and 6 are in a tie, and then 2, and then 4, and then 3, right? Does that make sense? Right? And again, since every bucket, if you now focus on the buckets, so this is bucket 3, contributed from ETH, and this is bucket 3, contributed from Zurich, and it's not in computer. So what we computed for bucket 3 is the sum of the things, right? So we did what we wanted to do here. Okay, so that's term at a time. Let's do it document at a time now. So it means that we start with document 1, ETH, computer, we are done. Document 2, ETH, computer, we are done. Document 3, ETH, Zurich, we are done. Document 4, Zurich, computer, we are done. Document 5, ETH, computer, and document 6. Note that if I did my job well, this is exactly the same thing. Doesn't matter if you do it term first or document first, because in any case, you're going to end up with the sum of the things for every document. Okay. So now, how much time does it take? What do we need to know to do for the scores? We need to sort them. What's the best sorting algorithm? That should be an automatic thing. What's the best sorting algorithm? N log n, right? N log n, that should be an automatic thing. You shouldn't even think about these things. There was a beautiful video of Barack Obama, by the way. He was asked a long time ago in a meeting with Google, like, what sorting algorithm should we be using? And then they thought they put it in a bad situation and said, no, I'm going to answer that. Don't use bubble sorts. So anyway, N log n for the sorting algorithm, the best ones. We're going to do this in linear time. Not N log n, linear time. How is that even possible? Because we need to sort things. How can we do something that involves sorting in linear time? Well, here's the trick. We are going to be using something that's called a priority queue. And in order to insert these things in a priority queue, it's going to take you linear time. Right? I'm not going to give you the details of that. It's just a structure that exists. It can be used for sorting. And the trick is that when you want to sort things, you just extract one by one from the priority queue, n times log n. And this is how you get your n log n, right? Using a priority queue for sorting. However, we are not interested in sorting everything. We only want the top 10. It's a search engine. We just want the top 10. So we don't care about everything. We just have a constant number of documents that we pick from. So this is why it takes linear time for the priority queue. And since we only extract a constant number of them, the log n goes away. That's magical, right? Linear time, we do that. Okay. It turns out that TF-IDFs are not the only thing in town that you can sum over. And there are alternate weighting systems. So I'm going to give you a menu because it's a bit like a restaurant menu that you can pick from. This one here is so here's how the menu works. It's like you have the starter and then the main dish and then the dessert. It's 3 parts. The first part is how do you handle the TF part? The second part is how do you handle the IDF part? And the third one is how do you handle the norm, the renormalization? So you need to make a choice for every one of these for the query and for the document. So it's 6 choices in total. So what's on the menu for the starters? So for the term frequency, WF is the generic variable, and then on the right you have the actually picked choice. So this is TF of the term in the document, right? So it's actually trivial because it's the identity. So this is why I drew that line y equals x, right? But the letter for that is n because there is a little code that you can use for that. So if you use the natural term frequency scaling, that's n. But here's another one. Here we don't actually take TF, we also pick a log, just like we do for the IDF, actually. So 1 plus the log of TF, so that gives us something more like this. And we call it L. That's the code for this. Or we can use something else that's called the augmented term frequency scaling that is given by this scary formula. It's basically just some sort of intermediate between a constant and the term frequency. So this is why you have this A and 1 minus A. So it gives you a curve more like this one here. Right? So if the term doesn't appear at all, you still have something that is positive. And if the terms appears very often, you have a bit less than the actual term frequency. So you basically just kind of rotate the curve a little bit like this, right? So you overweight the terms that are less frequent and you underweight the terms that are more frequent. Okay, that's A, the letter. Then we have the Boolean term frequency scaling, which basically comes back to the set of words model. You don't have an actual number, you just have a 0 or 1. That's called B. Boolean term frequency scaling, and you get this 0 or 1 thing. All right. By the way, I approximated things with a line and a curve, but these are not real numbers. These are integers, right, on the TF part. So that's, of course, just a pedagogical approximation. It's discrete. OK. And we have something that is even scarier, and I have no idea what that does, but it's called the log average term frequency scaling. And it looks like this curve that you see. It's also a way of logarithmically smoothing the thing, just like on the IDF part. Okay, so that's what's on the menu, right? N, L, A, B, or uppercase L. Okay, so that's for the term frequency. You can pick from this. Let's look at the document frequencies now. Well, the simplest is no document frequency at all. That was the naive thing we did at the very beginning when we didn't have any document frequency, right? We just summed over the term frequency. So in that case, there's nothing. So it's just 1. Okay. Then we have the one that we already covered, the IDF, that is the logarithm of the number of documents divided by the document frequency. So it goes all the way down to 0 if it's in every document, but it starts as log n if it appears only once. Right. 0 cannot be, because if it were 0, we wouldn't even be considering the term. Right. So this is why we don't have 0 here. All right. So n is for if there's no document frequency scaling at all. T is if you use the IDF. I have no idea why it's T, but yeah, probably they had a reason for calling it T. Then we have the probabilistic IDF document frequency scaling, that's called P. It's the max of 0 over the log of whatever, but basically what it does is that instead of ending with n, it ends with n over 2. I'm not going to tell you more about this, but we'll learn about it in a few weeks if we have time, and I show you the probabilistic information retrieval systems, because this is how we can actually compute this right there with a probabilistic approach. But I'm leaving it aside for now, and that's called P. Now, what about the normalization part? Well, first, you can decide not to normalize anything. So that's an N. Second, you can normalize with cosine. That's the Euclidean norm, right? So that's then C. Then you can also renormalize with the size of the documents in bytes. How many bytes the document is? Probably you want to add an exponent, A, for some reason. And there is another one that is a pivoted form of normalization that is, again, this A1 minus A thing. You just pivot the line a little bit, right? Okay, and what you end up with all these ingredients, you can cook your own thing, and you end up with a notation that's called the SMART notation, because it was part of a system that was called SMART back then. And what you have is 3 letters for the document weights. The first one is the term frequency, second one document frequency, third one normalization. And you can pick anything from the menu that I showed you. ATC would mean for the document, it's the augmented term frequency, the IDF because of T, and the Euclidean norm because of C. And then this is the query side. On the query side, we interpret the query vector with this sublinear term frequency, the natural document frequency here, and the byte size normalization of the query. And you can come up with any combination you'd like with these letters. And with these formulas, you're able to compute them. And there are exercises, I think, that the TA is prepared for you, where we give you documents and we ask you to compute the weights based on specific schemes that we give you, right? And then you just need to look them up. You need to know some of the letters by heart, not all of them, but N you need to know. N and B at the very least. Right, you need to know N and B. For the document frequency, you need to know N, which is the absence of any, and T at the very least, right? And then for the normalization, you need to know at least N and C, right? So this is the bare minimum, at least 2 letters for every position, right? The most important ones. The other ones we'll give to you if they are needed at the exam. Okay, just making sure also that the TAs hear me on that we remember to do that, right? The exam we will give any other. Okay. Oh, that's it for the parts on at least for part 1 on vector space models. Do we have any questions? Anything that is unclear? Anything you want to ask? No questions in the lecture hall. Do we have questions on Zoom? No question from YouTube? Anybody binge watching us right now? Want to ask a question? This is something I learned from the, there was a study run by the rectorates during COVID times and after COVID times. They realized that many students are actually binge watching lectures. So they basically don't attend during the semester, and then the end of the semester, they just binge watch like a Netflix series. Something I didn't know, but it's amazing. So if you're binge watching us right now, then hello to you. Okay. So let's stop here. I'll now switch to the next part where we improve on that and try to make it more efficient.